TM analysis of the parallel plate waveguide. We're going to do 4 things in this video. The first is perform analysis of the TM mode of the parallel plate waveguide. With that solution, we'll then look at it, we'll analyze it and talk about that. We'll visualize the different modes and then give an example at the end. TM analysis.
So here's our starting point. We are doing TM analysis, that is transverse magnetic. That means the Z component of H is 0. That means we are solving our differential equation for the electric field. And what was the Laplacian here, we're now writing as, expanded that into Cartesian coordinates, so we're looking at it as 2 partial derivatives with respect to x and y. And to remind us, once we find a solution for E naught Z, we will plug that solution into these equations to find all of the other components. Looking at our parallel plate, just like we did for the T analysis, we see that literally nothing happens in the x direction. The parallel plate does not change in the x direction. The mode does not accumulate phase in the x direction. Literally nothing happens. So any derivative in the x direction has to be 0. So if we go back to our differential equation, we can cross off that x derivative. Now we only have one independent variable left, so our partial derivative becomes an ordinary derivative. So this is the differential equation we'll solve to calculate the modes in a parallel plate waveguide for TM modes. So here's our differential equation. We could hand this off to a mathematician, not even tell them what the terms mean, and they could solve that for us and come up with our general solution. Just like I mentioned for the TE modes, we could choose our solution in terms of complex exponentials or in terms of sines and cosines. It's more conventional to go with sines and cosines here. And we have 2 constants, A and B. And we find these constants by applying the boundary conditions. Now something really fortunate is happening to us. We have our solution already in terms of the electric field. The Z component is tangential to interfaces, so we can just apply our boundary conditions directly to our solution. Remember, for the TE modes, we had a magnetic field solution. We had to then calculate the electric field solution in order to find those constants A and B. We don't have to do that here. We just apply our solution. So we look at the bottom plate. We set 0 in for y. Our sine term goes to 0, so we're just left with b cosine 0. Cosine 0 is 1, so we just end up with b. So b equals 0. Now we need to find a. So we will apply our boundary condition at the top plate. So at the top plate, we set in y equals d. Remember this b term, b was 0, so that's not even appearing here. We just have our a term times a sine. This has to equal 0. Well, if we choose a equal to 0, then that sets our entire solution to 0, and that doesn't make any sense. So it's not a that's forcing this to 0. It's the sine term that has to force this to 0. So the only way the sine term can be 0 is if its argument is an integer multiple of pi. So this kc times d has to be an integer multiple of pi. And we're going 0, 1, 2, 3. Notice there's a 0 here. It'll turn out we're allowed to have a 0 now. And later on we'll justify why that is. So we solve this expression for kc, and we get an expression m pi over d for our cutoff wave number. Let's look at our phase constant. So we had our original definition of our cutoff wave number as k squared minus beta squared. We solve this for the phase constant beta. We have the square root of the difference of 2 things. On the last slide, we had an expression for kc. We can plug that in, and we get an expression for beta. Again, we have this m, which is integers, and so what we'll do is we'll write beta with this subscript m to remind us that the phase constant is actually different depending on which mode we're talking about. And remind us again, for the TM modes, 0 is allowed because it does not force all of the fields to become 0. And we'll prove that in a little bit. So we have a TM0 mode here. It'll turn out, when we prove this, that that actually is the TEM mode. So here's our final solution. So we had a differential equation, we had a general solution. We found that b is 0, so this entire term disappears. We only have the sine term. But since it was the sine term that was 0 and a wasn't, a has to stay in this equation. So that just becomes the amplitude of our nth order mode. So here is the final solution for the electric field, and we tacked on this e to the minus j beta z. Now we can take that solution, plug it back into our equations to calculate all of the remaining field components, and this is where we end up.
Analysis of the TM solution.
Now let's talk about this TM0 mode. Does it exist? Well, we go to those field expressions we had on the previous slide. We set in m equals to 0, and what we see is we do have a magnetic field. We do have an electric field, so this is a valid solution. And it also turns out this is consistent with our TEM mode. This was much harder to derive. I might argue it's more rigorous. It was harder to derive, but it's our TEM mode. So TM0 is the TEM mode. Let's look at cutoff conditions. So our phase constant is the square root of the difference of two things. To be a guided mode, this needs to be a positive number. So this k squared has to be greater than kc squared, or k has to be greater than kc. And since that's the condition for a cutoff, that's why we call this kc term the cutoff wave number. And we need this to be positive to be a guided mode. So we have an expression for kc was m pi over d, where m is allowed to be 0 now. And so we can take this now and solve for cutoff frequency. And long story short, we have the exact same expression we had for the cutoff frequencies for the TE modes. This is really good because we can just use the one equation and calculate cutoff frequencies for both TE and TM at the same time.
I want to cover briefly these cutoff modes. There seems to be this misconception that if a mode is cut off, it doesn't exist, it's not important. And I want to sort of shatter that myth and bring reality into this because those modes are still there. They are not guided modes, they are something else. Let's get into that. So we start off with this expression for our phase constant, and it is the square root of the difference of two things. And we defined previously the condition for a guided mode is that this has to be positive. Well, that has to mean that if it's not a guided mode, what's inside has to be negative. Well, what on earth happens with that? What do we do with that? Well, if it is negative inside the square root, we can reverse those terms. That's essentially factoring out a -1. Then we can bring that square root of -1 out and just call it j. So we end up having a purely imaginary phase constant. And I have this double prime here indicating that's the imaginary component of the phase constant. Well, what on earth does a purely imaginary phase constant do? What does that mean? Well, let's ask. So we have our complex exponential describing a wave, e to the j beta z. Let's plug in this purely imaginary phase constant in here. So we just plug in a j beta double prime here. Well, when we multiply the two j's, we get a negative, and we get an e to the minus beta double prime z. Well, what is this? That is a decaying exponential. That is not oscillating. And we require oscillations in order to push power or push energy down a waveguide. So this mode is here. It does actually extend some distance down the waveguide, but usually very short, and it's pure decay. It decays quickly. Another interesting subject is the velocity of these guided modes. Well, how do we get the velocity? We start with how the phase constant is related to the effective refractive index of the mode. The effective refractive index, if we had an infinite medium and an electromagnetic wave buried in this medium with this effective refractive index, it would propagate at the same velocity as a guided mode with this phase constant. So that's the meaning of the effective refractive index. We also know that effective refractive index quantifies the speed of something. The speed of light divided by this refractive index tells us how fast that is traveling. So we're assessing the speed of a guided mode through its effective refractive index. Well, let's replace beta with our expression for the beta. Then we'll solve that equation for the effective refractive index, because remember, this is how we're assessing the speed of the wave. We have this K naught sitting on the outside because it was over here on the right side of the equation multiplying the effective index. Let's bring the K naught inside the square root. When we do that, we have this K over K naught, and it'll turn out this will be the refractive index of the medium, not the effective refractive index. It's the refractive index of the medium. There's additional things happening because it's inside of a waveguide that would make the effective refractive index of the guided mode different than the refractive index of the medium filling the waveguide. So that's just refractive index squared now. To simplify this a little bit, let's say we have an air-filled waveguide or vacuum-filled waveguide. That means the refractive index inside the square root here is 1. Well, 1 squared is just still 1. So the effective refractive index, quantifying the speed of the guided mode, is the square root of 1 minus some number. Now this number here will always be a positive number, so we're always subtracting a positive number. That means the argument inside the square root is always something less than 1. And the square root of something less than 1 is still something less than 1. So if the effective refractive index is less than 1, what does that actually mean, right? Because the speed of the wave is the speed of light divided by that effective refractive index. If that is less than 1, that implies the velocity of a guided mode in this parallel plate waveguide is faster than the speed of light, faster than light in a vacuum. How on earth could this be? Did we make any mistakes in the math? We did not make any mistakes in the math, I'll tell you that. And just as a teaser, I'm not going to answer this, but this does have a clever answer, and it'll answer whether you can actually get faster than light propagation inside of a waveguide. I've heard many, many, many people claim that that's possible, and this is why. I'll just tell you, it's not actually possible.
Let's think about the characteristic impedance. Characteristic impedance is defined as the amplitude of E over the amplitude of H. And we now have expressions for the electric and magnetic fields that we can plug in here to get an expression for the characteristic impedance. And since we've done the wave analysis here, we also have an expression for our phase constant. So we can actually calculate the characteristic impedance of our TM modes.
Visualization of the TM modes.
Here's a visualization of the TM0 mode, which, by the way, is the TEM mode. It has a perfectly uniform field from plate to plate. The electric field's pointing straight from one plate to the other, not in an angle or anything. And the magnetic field is in the X direction. We can look at the TM1 mode. Now let's look at this a little bit more carefully. When we looked at the TE modes, I said we could interpret that subscript as the number of bright spots that we would see between the plates, or the number of peaks of the field. Now if we look at this, it seems like we see 2 peaks, even though this subscript is 1. because we see a peak up here, then it goes to 0, then another peak. And really what we're looking at is half of a peak at the top and half of a peak at the bottom. So really overall it is just one peak, and that's tricky and all that, but in fact we still only have one bright spot. It's just been split to the top and the bottom. So keep that in mind, that your bright spot could be split. The TE2 mode. Now the fact that the top and the bottom are split is a little bit more apparent, because we can look at the width of a full bright spot, and clearly what's at the top and the bottom is just each half of a bright spot. So overall we have two bright spots, and that's the TM2 mode.
Let's do an example.
Let's do an example. Very similar to what we did before. Now we have a width of 2.48 millimeters. Remember, this was our design to make this 50 ohms. So 2.48 has a plate separation of 0.5 millimeters. Dielectric constant is still 2.3. Now I'm going to ask the question, what is the bandwidth of this waveguide when it is used as a transmission line? So when I say when it is being used as a transmission line, that means we only want the TEM mode. We don't want the TM1, 2, 3, or any of those higher order modes. We only want the TEM mode. Or if I'm talking now just in terms of TETM, it's the TM0 mode. And so we don't usually ever want a multi-moded transmission line. So we can calculate the bandwidth by finding the cutoff of this next higher order mode. So the TE and TM modes have the same equation, so we can check them at the same time. That's super convenient. So let's calculate the TE1 and TM1 mode. And we plug in m equals 1 in our cutoff frequency equation. And we have all the numbers. We have speed of light, we have our mode number, plate separation, relative permeability, relative permittivity, and we end up calculating a cutoff frequency for the TE1 and TM1 modes of almost 200 gigahertz. That means this parallel plate transmission line we designed will act like a transmission line and only support the TEM up to 200 gigahertz, or 197.6 to be exact. Above that, the TEM still exists. It's just that now that there's other modes that also exist, we could accidentally be exciting them and bad things could happen. So the bandwidth of this guide is 197.6 gigahertz. Conclusion. Here is a big, ugly summary of all the different equations for these various different parameters that we might want to do waveguide analysis, wave designs. Not a whole lot really to discuss here. It's just a summary of a bunch of equations, the field values, the different waveguide parameters if you want them. I've plotted the first three order modes. We have equations for the TE0 mode. We know that it's not a physical mode. I went ahead and plotted them and X'd them out to remind us those don't actually exist. Our TM0 mode, notice everything is straight and uniform. That is clearly the TEM. And here's plots of the other modes. And it's a little bit more obvious here how we are looking at two half bright spots. So there's our modes. Here's a summary of our analysis. We have our field solution, so this is what the fields look like for the TM modes. We have our phase constant, same equations as for TE. The only real difference here is that M is allowed to be 0 for the TM modes. It wasn't for the TE modes. And that's, of course, the TEM mode when we set M equal to 0. Cutoff frequency has the same equations for TE, and we have an expression for the characteristic impedance of the TM modes. So the TM0 mode is the TEM mode.
From the bottom of my heart, thank you so much for using EMPossible. I want to create more videos, and I want to continue to improve how electromagnetics and computation is taught online. To do that, it will really help me if you can like this video and subscribe to our channel. I also want you to know we have a lot more content that you may not be aware of. See everything we have to offer at EMPossible.net.